You know, this is often called the most beautiful formula in all of mathematics. But what if it's not a human invention at all? A really fascinating new paper is suggesting that this elegant equation, well, it isn't some clever trick we came up with. It's actually a fundamental blueprint for reality itself.
So here it is. This is Euler's formula. And yeah, for centuries, we've basically seen it as this magical, super elegant tool. But what if it's more than that? I mean, what if it's not just a useful description of reality? What if it's something reality itself demands?
And the wild part is, this formula is, well, it's absolutely everywhere. I'm talking about the electricity flowing through your walls, the quantum mechanics of atoms. Seriously, if something in the universe oscillates or rotates, you can bet Euler's formula is right there, working behind the scenes. It's, unreasonable effectiveness. That's the real mystery we're going to try and crack today.
Okay, so Section 1, a new physical origin. And this is where we start trying to solve this mystery. We're going to dive into this really radical new paper by Sun-Yun Hong that, well, it proposes a completely new physical origin for the formula. It basically flips our entire understanding on its head.
Now, the paper's core claim, it's a total perspective shift. Here it is. It argues that we didn't invent this formula to describe rotation. No. Instead, the fundamental nature of physical rotation in our universe is what forces this exact mathematical structure into existence. Let that sink in. Physics is dictating the math, not the other way around.
So, to build this argument, the paper has to introduce this really foundational concept. They call it the J-cell. Just imagine for a second that the universe is built from these countless, tiny, perfect little spinners. And these aren't particles like you're thinking. No charge, no mass, none of that stuff. They have exactly one property, the angle they're rotated to, their phase. That's it. A pure, fundamental unit of rotation.
Right, so Section 2, the rules of rotation. The big question is, how do these super simple spinners build, well, everything we see? The paper argues they just have to follow 3 simple, completely non-negotiable rules. These are the fundamental rules of rotation.
Okay, let's break down these 3 rules. First up, isotropy. All this means is that each spinner is perfectly symmetrical. There's no special up or down or left or right in space. Rule 2, local coupling. This just means they only interact with their immediate neighbors, and all they care about is the difference in their rotation. And finally, Rule 3, composition. This is super intuitive. Rotations have to add up. A 10-degree turn plus a 20-degree turn has to equal a 30-degree turn. Makes sense, right?
So now we get to Section 3, why the formula is forced. And it's these 3 simple rules, these are what create that whole forcing argument we talked about. They act like these really tight constraints, basically backing us into a mathematical corner where there is only one possible way out.
So, the whole thing boils down to this one crucial question. What's the simplest, most efficient way, the most minimal mathematical language you could possibly use to write down a rotation that follows all 3 of those rules?
Well, if you try to use simple, regular numbers, the math just gets messy. It's super clunky. I mean, think about it. A 350-degree rotation is basically the same as a negative 10-degree rotation. Simple addition just can't handle that kind of cyclical nature without a bunch of awkward workarounds. But if you use complex numbers, it's completely effortless. That simple rule, rotations add up, becomes another simple rule we all know, exponents add up. It's like complex numbers are the native language of rotation.
And that leads us to the paper's really stunning conclusion. The complex exponential, e to the I theta, it isn't just some convenient choice we made. It's the only mathematical language that satisfies all those physical rules simply and completely. It is, just like the paper says, structurally forced.
And this brings us to the absolute core insight, and it's summed up perfectly in this key quote from the paper. What it's really saying is that the complex exponential, that represents the pure, unadulterated rotation, that's the real thing. The cosine and sine that we see in the formula, they're just its projections.
Okay, let's really break that down, because this is a huge idea. It's saying that the pure rotation, the e to the I theta part, that's the fundamental reality. So what about the cosine and sine we all learned about in trig class? Well, they aren't fundamental at all. They're just the shadows that this true rotation casts on the x and y axes when we try to measure it.
And get this even gives a new physical meaning to the number I. So forget that confusing name, imaginary number. In this framework, I isn't something you imagine at all. It's a physical command. It's literally the instruction for rotate 90 degrees counterclockwise. And that's why I squared is -1.
Two 90-degree rotations is a 180-degree turn. It's not some abstract math trick. It's a description of a real physical action.
All right, so section 4, from cells to waves. Up to now, we've just been talking about one single spinner. But what happens when you start linking them together in a chain? How do these tiny individual rotations build up to the world we actually see?
Well, the way it works is actually beautifully simple. One cell rotates, and because it's coupled to its neighbors, it passes that little bit of rotation along the chain. And what do you call a propagating chain of interacting rotations? You call it a wave.
And this is exactly why this physical origin story is so powerful. It doesn't just describe waves, it generates them. It explains why the math we use for wave physics actually works so well. You know, tools like Fourier analysis, the ones that break down complex signals into simple sine and cosine waves, they're not just clever techniques. They work because they're speaking the fundamental, native language of these underlying rotating cells.
Okay, but here's the really cool part. When you actually derive the wave equation from this model of discrete cells, something unexpected pops out of the math. A tiny little extra term appears in the equation. And it's a term that simply wouldn't be there if the universe were perfectly smooth and continuous.
The paper calls this k to the fourth term a structural residue, but I like to think of it as fossil evidence. It's a mathematical fingerprint, a ghost in the machine, that hints that our smooth, continuous reality is an illusion, emerging from a deeper, discrete cellular structure governed by rotation.
Okay, section 5, structure, not a trick. Let's bring this all home. The big takeaway here is that Euler's formula, it isn't just some clever trick we use to solve problems. It is the structure of the problem itself. And this is all summed up in what I'd call the paper's master statement. It pulls the entire argument together. It basically says that the familiar Euler formula we all know and love, that's just a projection, a shadow of this deeper primitive thing. And because of that, things like plane waves in physics, they have to take on this exponential form. It's not a choice, it's structurally forced. And this leaves us with a truly profound shift in perspective. The takeaway here is that math, it isn't just a tool we use to describe the universe. It is the structure of the universe. We're not inventing it, we're just discovering the grammar of reality itself.
So, I'll leave you with this question to chew on. If math's most beautiful formula isn't a trick, but is actually undiscovered physics, what other so-called math tricks are out there, just waiting to reveal some deeper, fundamental part of our universe?